Welcome back. This is session 4 of the EasySpin Academy 2020. In this session, we're going to look at solid-state EPR. So for solid-state EPR, the dedicated function is called Epr, which is an abbreviation for powder EPR. Epr allows you to simulate spectra of any solid, of crystals, of powders, and of frozen solutions. Let's start with a very simple example. Again, let's clear everything out here. Define a spin system with now 3 G values. Let's say the Gx is 2.10, the Gy is 2.10, and the Gz is 2.56. This will be typical for a nickel 1 species. Let's add some broadening, convolutional Gaussian broadening with LWPP. Let's say 1 millitesla for simplicity. This is exactly the same as we did for the liquid state simulations. The sample definition, all the sample definitions work exactly the same. For the experiment, the minimum required is the microwave frequency. Let's stay again at X band, 9.5 gigahertz. All we need to do now for the solid state spectrum is to call Epr for the system and the experiment. And if we press enter, control enter, we'll receive the simulation. As you can see, there's the powder spectrum with a sharp positive feature for the Gz value, 2.56, and then the up and down feature for the Gx and the Gy direction. So Epr works exactly the same way as garlic, except it uses a different theory, and it assumes that you want to simulate the solid state spectrum. If you don't tell it to simulate a crystal, it will always simulate the powder or a frozen solution. So meaning that it assumes all the paramagnetic molecules are randomly and uniformly distributed in orientation within the sample. You can also plot the absorption spectrum by saying x.harmonic equals 0. So this would be absorption spectrum. Again, if you run this section by pressing Control Enter on Windows or Command Enter on Mac, we get the absorption spectrum. Now you can see actually the absorption goes from about 265 millitesla all the way to above 320 millitesla. If you had a look at the first derivative, right, you would think there is no absorption here in the middle, but in fact there is. The absorption just has a very slow slope, a very shallow slope, meaning that its first derivative is essentially very close to 0. Okay, this is the absorption spectrum, and we can of course ask Epr to give us back the field and the spectrum and just plot it ourselves, or if you want to export it or save it in a file. And voila, it is. It's not as decorated, the plot, as Epr does it, but that's how it works. So there are two major things that in which simulations in solid state differ from liquid state. First of all, you always need to include the full G tensors. In a liquid state simulation, you could supply this type of full G tensor, but garlic would just then take the average and use the average G value for the simulation. But for solids, you always have to specify the full tensors because the molecules don't move, and so you will have anisotropy. The spectrum will depend on how the molecule is oriented in the spectrometer. And since you have all orientations, we're going to sum over all these different spectra to give the full, what we call the powder spectrum. So the second difference to the liquid state is that now we need to sometimes take into account different broadening mechanisms. We actually have to think about the physics behind broadening. So in a frozen solution of let's say a small complex, in our case, let's say this nickel complex, when you freeze them, and the nickel is coordinated by some external, some ligands, the freezing will result in strains and different solvent crystallites that kind of push and pull on the ligands. And as a consequence, they will change the local geometry a little bit. And these small random changes to the local geometry are going to be different from one nickel complex molecule to the other in your sample. And these small structural changes, of course, have electronic effects, and they will slightly perturb your G tensor. So from molecule to molecule, the G tensor will have slightly different values. Or, as we say, the G tensor has a strain, or it's distributed. And EasySpin can include this type of broadening very easily. And if you have multiple, the G tensor is not a uniquely defined number, but a distribution, it will broaden your spectrum. Right? Let's do that. So again, we remove the convolutional broadening, LWPP, which is just, broadens the line in the spectrum without thinking about the physics behind it. And we're going to add now a so-called G-strain. And G-strain takes three numbers, one for each of the G values, basically gives the width of the distribution of that particular G value. Let's put in 0.002. Actually, no, I'm going to use some different G values here. 2.00, 2.19, and 2.37. Okay. And then 2.03, and let's say, what did I prepare here? 0.1. So these are the mean G values of the distribution. So on average, the average Gx value is 2.00, and the distribution of Gx values among those molecules in your sample is 0.02. This is the full width half maximum of the distribution. You can see the Gx value is pretty narrowly distributed, Gy is a little broader, and the Gz in this particular simulation we're going to assume to be the broadest. If you run this again with Control-Enter, you will get a broad absorption spectrum. You can see a kind of a rhombic spectrum with three features here, like the rising feature, a peak, and a dropping feature. This is the first harmonic, the absorption. Let's go to the first harmonic. Okay, see the field range. EasySpin wasn't quite able to figure out the field range to come back to baseline, so we're going to add the baseline ourselves with giving the field range x.range equals, maybe we should go down to about maybe 270 and up to 350. So from 270 to 350 millitesla. And let's run this again with Control-Enter or Command-Enter. Voila, now we've got baseline on both sides. Now what you can see is that the low field feature is much broader than the high field feature. The low field is from the highest G value, which is 2.37, and that's the one we broadened the most. And the high field feature is from the lowest G value, 2.00, and that one had the smallest broadening, right? So as you can see, it's physically possible that different parts of the spectrum have different broadenings, and that's a result of this orientation-dependent sensitivity of the G values to structural distortions. So these are called strain broadenings, and they're available not just for the G tensor, but also for the hyperfine tensors and the zero-field splitting tensors, and also, I think, for the quadrupole tensors, but I'm not entirely sure. And they allow you to model this kind of structural heterogeneous distribution of structures. There is one big assumption behind these G-strain strain broadening models in EasySpin, and that is that these distributions are narrow relative to the mean. So for example, 0.02 is small relative to 2.00, right? It's like 1%. As soon as the strain distribution width hits maybe 5% or 10% of the actual mean value, then the approximation within EasySpin does not quite work as well anymore. And you're better off writing your own for loop, basically simulating spectra with slightly different G values and adding them all up. And that will give you the same result. And for larger distributions, that will give you a correct result. Whereas EasySpin assumes the distributions are fairly small. Next, an important thing for solid states are tensor frames. Okay, so let's take a simple example. I'm going to just pick something I've prepared. It is a rhombic G tensor, spin 1/2, one coupled to one proton, and the hyperfine coupling is rhombic, so three different principal values and large, 60, 120, 200 megahertz. And we just use convolutional broadening. Let's go back to that simple phenomenological broadening. Let's run this at X band with a certain range. And let's simulate this and call Pepper with sys, exp, and see how it looks like. I need to plot it. That's why it's not showing up. Plot b, spec 1. Voila. So we see three groups of line pairs. The splitting is the low field is largest, the splitting in the middle field, and the splitting at high field is the smallest. We see a little bit of simulation, what we call simulation grass here. These are not physical features. This is just an effect from not having enough orientations when you do the powder averaging. But we'll get to that. But for now, this is good enough. And now, so right now, this assumes that the G tensor, given here G, and the A tensor, given here with A, they are collinear, which meaning the X direction for this G value is the same as the X direction for this A value. Right? One way to think about it is each tensor has some sort of ellipsoid, kind of a potato. And if these ellipsoids are oriented the same way, then they're called collinear. And that's what we have right now. Now, in reality, in molecules, these tensors all they're tilted relative to each other, and you might want to specify that tilt. And that can be done with for the hyperfine tensor with something called A frame. So sys.A, because it's a hyperfine coupling, and then frame to specify the orientation of that tensor relative to a molecular reference frame. So the A frame, let's say 0, 0, 0. That's basically saying it's aligned with the G frame, aligned with the G tensor and with the molecular frame. And these are the three numbers of the so-called Euler angles. And there are in radians, not in degrees. Okay, so if you press Control Enter, nothing changes, right? Because if you don't specify an explicit orientation, everything's assumed to align with the molecule. And so EasySpin implicitly has this notion of a molecular reference frame, which is kind of an XYZ frame system that's attached to the molecule in a fixed orientation. So if you turn the molecule, the frame rotates with that molecule. Right? And what you do when you specify these frames here for A frame is you specify how your tensor is oriented relative to that molecular XYZ axis, the molecular reference frame. But more about that in the next session. Let's just now tilt the A tensor and observe the spectral changes. I'm going to copy paste this here. I'm going to now change the first Euler angle to pi over 2 and simulate a new spectrum with that and plot that together with the first spectrum. Control Enter, and voila. You see what has happened is that some values change, right? The orientation of the hyperfine tensor changed so that a different hyperfine splitting is now observed for a given G value. So this is how tensor frames work. Another thing we can do is, if we go back now, and we can get transitions out separately. And, that is called opt.output equals separate. Now let's look how this looks like. Pepper, we're going to just call Pepper again with whatever system we just have defined, and look at, we have to also feed in the options now. Again, the third input is always simulation options. In this case, it's just telling us that the output should be in separate transitions. What you see here now, previously we had one spectrum that had these 6 features, right? 2 in the low field, 2 in the middle field, and 2 in the high field. Now we're getting at least, what is it, 1, 2, 3, 4 separate spectra. So these spectra are this different separate transitions in the EPR spectrum. The 2 intense ones are the allowed ones. Let's see if we can pick them out. Here's the red one, and then we have the orange one. But we also have a blue and a purple one, and those are very weak. If you look, we can zoom in. Those are very weak. These are forbidden transitions. So this shows you that EasySpin always, when you use Pepper, it always simulates the allowed and the forbidden transitions. Because in some cases, these forbidden transitions are actually quite intense. So that's how you get separate output. Now let's revisit this problem of orientational averaging. Let's go back to a much simpler system to make this more clear. And the simple system here is a G value, an axial G value of 2, 2, and 2.5. Some convolutional broadening, we're at X band, and we're looking at the powder spectrum. If I run this, I'm getting a nice axial spectrum, but if you zoom in, you can see there's some wiggles. These wiggles are what we call simulation noise or simulation grass, and it's a problem. It appears when you don't have enough orientations in your averaging. Because in order to simulate the powder spectrum, what EasySpin does, it simulates spectra for many different orientations and adds them all up. So how to increase the number of orientations? That's a simulation options. And the option is called opt.n knots. The number of knots on a sphere. And we can start out with a very small number to see how bad it can get if you have only 10 orientations. So I'm writing 10 here, and I'm adding the third input to Pepper. Third input is always simulation options. Control Enter. And what you see now with 10 orientations, we get some artificial peaks throughout the entire spectrum. Let's increase that. Let's go from 10 to 100. And you see in this case with 100 orientations, we're very much converged. There is not a hint, maybe there's a tiny, if you zoom in really close, you can still see there's a little bit of simulation noise, but that should be gone as soon as you go to like 300 knots. But as you probably might guess, using more, increasing the number of knots also increases the simulation time. So always try to optimize the number of knots. Keep it at a minimum. That gives you a smooth spectrum without wasting simulation time. You don't need more orientations than necessary. So 100 is probably a good choice here. You can see EasySpin is able to simulate a full powder spectrum with just 100 orientations. In your sample, you have probably 10 to 12 or 10 to the 13 different orientations from your 10 to the 13 molecules. But 100 is sufficient to get a smooth spectrum. Okay, field and frequency as the next topic. So Pepper simulates a solid state field swept spectrum, but it can also do a frequency swept spectrum. Let's take the examples from above. But now instead of just specifying a fixed microwave frequency, we can specify a fixed field. X.field, let's put in 350 millitesla. And now if you call Pepper with this particular sample, with this particular experiment, it will actually simulate a frequency swept spectrum for a fixed magnetic field. Control Enter, and voila. We see it now, the x-axis is a frequency axis in gigahertz. And if you're at 350 millitesla, the spectrum for this particular sample goes from 9.7 gigahertz all the way to 12.2 gigahertz. Now, of course, nobody has this type of X-band spectrometers, but you know, there might be some broadband spectrometers that do frequency sweeps. That actually there are, and it's also very useful to look at frequency swept spectra if you're doing pulse EPR measurements, for example, ECM or ENDOR or DEER, because those pulse EPR experiments are done at constant magnetic field. And this frequency swept simulation lets you look at the EPR spectrum that you actually have in your sample for that fixed magnetic field. Okay, as you can see, we see some steps here. These steps are not simulation. They are simulation graphs, but we have a problem. Our line width is too narrow, unrealistically narrow. And the reason is that LWPP for a frequency swept spectrum is now interpreted in megahertz. So you have to change that to a much larger number because half a megahertz is an unrealistically small broadening. So let's change that maybe to 50 megahertz. If you run that again, now we get a more realistic broadening in your frequency swept spectrum. So finally, for the solid state simulations, one more thing I would like to mention is the algorithm that's underlying it. Just like for garlic, for liquids, you have a choice of which algorithm to use. And by default, Pepper uses the slowest but most exact one. But you can reduce the theory level to a more approximate treatments to speed the calculation up. And if you have a lot of nuclei in your spin system, then this is sometimes required to make it workable on a computer. But you always need to check whether the approximation is actually valid or not. So let's start out. Let's do, what did I do here? Spexis. I think we can take the same spin system. Let's go back. Let's take this spin system here. Clear, and now let's actually go down to S-band. which is about 3 gigahertz. I'm going to now explore several simulation methods. Opt.method is again the field, and the most accurate method is called matrix because it performs matrix diagonalization of the spin Hamiltonian matrix. Let's then simulate this. We spec 0 equals Pepper and provide the sample, the experiment, and the simulation options. Then we're going to copy paste this and just change the theory level twice. We're going to use perturb 1, which is first order perturbation theory, and perturb 2, which is second order perturbation theory. And call this spec 1 and spec 2. Finally, we're going to plot all of this, B spec 0, B spec 1, B spec 2, and add a legend for matrix, perturbation theory 1, and perturbation theory 2. And if you run this, in this particular case, you don't see a lot of difference. But if we start adding nuclei, you will see that the treatment will be very much different. And you need to explore, if you need to reduce your simulation time because you're running out of time in memory, you can go from matrix to perturb 1 and or perturb 2. But then you always need to at some point check whether your perturbation assumptions are valid. So this concludes a brief initial overview for solid state EPR. In the next session, we'll talk a little bit about frame orientations and Euler angles. And in the session after that, we'll swing back to solid state EPR simulations. And for now, please look at the script, go through the exercises or start looking at exercises or just take a break. I'll see you back. It is now 9:52. I'll see you back at 10:10, which is in about 18 minutes. Until then, bye.